Yeah, welcome everybody to our lecture today within our course, Deep Learning with Python. We have the great pleasure today to hear about deep learning problems and challenges in remote sensing and geographic information systems by Dr. Lingli Zhu. Dr. Lingli Zhu received a master degree in photogrammetry at the Helsinki University of Technology in 2007, and then a doctoral degree in the field of remote sensing with a minor in information technology at the same university, but then named Aalto University in 2015. Currently, she works as a chief specialist in map production and research manager in the Finnish Geospatial Research Institute of the National Land Survey of Finland. Thanks a lot, Lily, and please take it away.
Thank you. Now, today I'm going to talk about the deep learning problems and the challenges in remote sensing and the geoinformation systems. So there are three topics in this talk. First is the introduce the remote sensing and the GIS in very brief, like take a few minutes to have a look what's the remote sensing and the GIS, and also talk about the current. I'm leading this autumn project, which is using deep learning technology, and then the last part, also the most important part, we will figure out without making physical contact with the object, and the sensing means acquisition of information by using sensors. So remote sensing mainly dealing with the different spectral bands from the visible light like RGB. Currently, a lot of images we use the RGB from the cameras, and also from a remote sensing, we also dealing with infrared and some other channels. And there are two types of sensors: passive sensors and active sensors. In passive sensors, like a camera, I think everybody is familiar with the camera currently. Even on the mobile phone, on your phone, you use the camera to shoot the pictures in the daily life. But from remote sensing, we have different type of the images, like panchromatic image, multispectral image, hyperspectral image, and from the active sensors like LiDAR. So difference between passive sensors and the active sensor means, like in the LiDAR system, you in the sensor you have the you need the sensor will launch or emit a light source towards the environment or surroundings. Then the pulse will bunch off and return to the sensors. So from this time you will record the time and then can calculate the distance between the sensors and the objects. So that's the basic principle of the LiDAR, how it works. And then we talk about the sensor, remote sensing sensors and the platforms. The first row shows the sensors. As we see, when we talk about camera and from the remote sensing point of view, we have different types of camera. For example, like a ladybug camera, which had 5 cameras in one system. Also currently, like a mobile phone has the camera. So any kind of sensors, when you take images from the surroundings and without contacting the objects, so we called it remote sensing. And also currently, I think everybody is talking about autonomous driving, and it comes in coming years. I think it will come in this technology. And on top of the roof of the cars, you can see a lot of sensors. And the most typical use is the cameras and the laser scanners, which we also call the laser scanner LiDAR. So it's basically it's the same thing, like LiDAR and the laser scanners. So on top of the car, you attached a lot of sensors, several LiDAR and several cameras to acquire the information from the surroundings. From the platforms of remote sensing, I think everybody knows about the satellite. And the satellite, you can put the camera on satellite, and also, of course, this camera, it's a very special camera. You can like see through. For example, you use the microwave band, then you can see through from the cloud. So target the surface of the Earth, and also aircraft. You can put the cameras or laser scanners on top of the airplanes, and also you can put those sensors on top of UAV. And also you see the right corner, there's the sensors laser scanner on top of the mounted stick, kind of tripod, and it's you can sense the surroundings by just standing there, and then rotate with the 360-degree rotation, and then you can get the information from all your surroundings. So mainly we're dealing with the sensors and the different platforms from the remote sensing. Since today we are talking about the deep learning technology, so we must talk about the data set. What kind of data set from the remote sensing, from the sensors? So first is images, like satellite images, aerial images, or terrestrial images. So those are kind of remote sensing images. And also point cloud, which typically from the LiDAR system. So if you put the LiDAR on top of your AV, you get the this kind of view, like usually it's 45 degrees, or this kind of a view to the surface of the objects. And also if you put the LiDAR system on top of the aircraft, so you will get the top view of the surface of the Earth. And also, if you put the LiDAR system on the mobile like a platform, like cars and vans and any kind of mobile, even currently, I think there's a system like you can put on your backpack with the LiDAR system, and when you walk, and you will get the you will scan the surroundings and get the information, get the point cloud of the surroundings. So let's talk about characteristics of remote sensing data, which is quite, even we talk about images, like also remote sensing in computer science, but I think it's quite different. From remote sensing, we have very large format image. It can be 30,000 times 30,000 pixels, very large format. And also we have a multi-channel spectral band, up to 256 channels. Also multiple data types from the diverse sensors, and the multi-temporal data, like you can scan or measure the environment, like a daily, weekly, monthly, and seasonally, and yearly. And if you measure the data from the springtime and the summertime 2 times, and you compare the data sets, you will see it's quite different, because summertime, the environment with a lot of trees and the vegetations, but the springtime can be, in Finland, can be a lot of snows cover the surface. So it can be quite different even with the same area. And then have a large coverage of spatial data, like covering the whole country or covering the whole world. So typically, like a satellite image, it's covered with a large coverage. So satellite image can like monitoring a certain area of the Earth. For example, it rotates with the same speed as the Earth, and also there's a type of satellite with the same speed with the Sun. So you can monitoring the whole world as the surface of the Earth. Then we talk about the GIS data. GIS data, basically, it's like from a remote sensing data, and then you get information for the GIS data. So it's a kind of a connection between the GIS and the remote sensing. So GIS means Geographic Information System. So it is a computer system for capturing, storing, checking, and displaying data related to positions on Earth's surface. So GIS connects data to a map, integrating location data with all types of descriptive information. So from GIS data, it allows users to visualize the spatial context on a map or as a map, or allow users to make a query in a spatial context. And the characteristics of the GIS data about spatial coordinates, for example, locations like longitude, latitude, and height, and XYZ coordinates, and with the temporal information, like from which year this data is from and which date you acquire this data set. And this is usually it's a kind of tags on the data sets. You might mark like this data from which day, which year, and like this details from the GIS data. And also GIS data with the attributes like a class. For example, this class is for the use different use of land. For example, for agriculture use or for the other forestry or something like that. So it's this data usually with this kind of mark in the data sets, and with a spatial relation like distance and proximity between the different location, and with a dimension like point, lines, polyline, polygon, and area and volumes. So GIS data usually cover those characteristics. Here is we in general view about the type of GIS, which has vectors and rasters. I think all of you should maybe understand about what's a raster, what's a vector, because in deep learning, raster means like an image, vector means labels. So it's a kind of format which we use quite often in deep learning technology. So then we talk about the Atom project. So this project is basically is about advanced technology for national topographic map updating. So we call it Atom project. So why did we launch this project? Why do we need this project? So here is the background or motivation of the project. Currently, topographic map was updated by stereo model of area images with many operators. So in National Land Survey, currently we have almost 100 operators working on the same like a stereo model and check where which area has changed, and this kind of manual work. So it's a labor-intensive work. And since last year, and we launched the new area imagery program. So this new area image like annually covering the 1/3 of Finland. So one of the applications is to be used for topographic map updating. And also new LiDAR data program started from last year also, and covering 1/3 of area in Finland annually to get the very accurate point cloud data. And then another reason is we had a kind of annual meeting with the neighbor countries and the other national mapping agency in Europe. And then we noticed like since 2016, the neighbor and the other European national mapping agencies have started to develop the AI-based method for topographic map updating. So we need to obtain our own knowledge in AI for mapping agency and catch up the development of the other countries. So here we talk about topographic map, and I can explain it in a few words. Topographic map has the features with different type of objects. For example, the buildings, road, like transportation, kind of different type of road with very detailed information and detailed class of the road. For example, this highway or this pedestrian and this kind of information, and also buildings and bridge, for example, bridges and the power lines and a lot of all kind of objects on the surface of the earth or on our surroundings will be covered into the topographic maps. So so today we mainly talk about this topographic map updating in this autumn project. So this is basically from the view of National Land Survey point of view. And then if we talk about this AI from the nation point of view, so the Finnish Ministry of Employment and Economic Affairs states that if we embrace AI and use it to its full potential, so Finnish GDP per capita can grow by 3% per year up to 2030, compared to 0.8% if not using AI. So that's the reason why we launched this project and was supported by the Ministry of Finance. So this project started from the beginning of this year, from the January, and it will end at the end of next year. So we are going to use the deep learning technology for national topographic map updating. And we are focusing on the three types of objects, buildings, roads, and hydrographic features. So about hydrographic features, mainly we focus on the ditches and the streams. So those objects updating will be the main topic in this project. So in this project, we planned in 4 work package. The first work package is collecting the training data sets of the buildings, roads, and hydrographic features. And then we use a deep learning method for buildings, road change detection, and also deep learning method for hydrographic feature change detection. And the final result will be tested and evaluated. So during this project, we are going to study different technology of the deep learning method, like deep convolutional neural network, multitask learning technology, and the transfer learning technology. Here, let's have a look at the current status of this project. And in this project, we have produced more than 30,000 square kilometers through also photos and digital surface models, and more than 2,000 square kilometers building training data sets, also more than 1,000 square kilometers road training data set, and 36 square kilometers hydrographic features training data sets. Currently, those training data sets are available. And from the technical development point of view, currently we got quite a good result from the convolutional neural network, which we use the UNet, and also transfer learning technology. And for multitask learning technology, it's still under development. And from the right figure, you can see there are two figures, and the left one shows the was from the statistics of the time allocation in a deep learning or AI project. So they divided this into 3 parts. So the major part is about get training data ready, and then experimenting and the coding. So from according to this statistic time allocation, so I made another evaluation about our project, where we are. So the green one shows we have done, because like this training data sets, mainly we got most ready, except the part of the hydrographic features, which we will get more training data at the beginning of next year. But the other part, I think we have enough kind of a training data set. Then from the deep learning development point of view, we had some result experimenting has done, and also made some codes for the development. And this computational environment in this project, we use the CSC, which is the high performance computing, and this is kind of free for the research purpose. So this project, it's a research project. So we currently got a great support from the CSC. And let's have a look at the training data set which we have. We have this two-dimensional vector data plus images and for the buildings. It's we mark these vectors with very detailed information, as you see, not only rectangles, kind of boxes, but also very detailed information from the outline of the buildings. Also training data from this 3D LiDAR point cloud for buildings. The left one is the original LiDAR data set, and the right one is the classified the buildings from the LiDAR point cloud. And here is also the same, the 3D LiDAR point cloud, and with the left one, it's a training data set, which not only buildings, but also cover the environment, the surroundings of the buildings for the training data. Then here we also have the digital surface models, which got from the point cloud. So we classified those information, because this is a 3D information, not only XY, but also Z values covered in this digital surface model. So we use the height of the point in the unit. Here is the road training dataset. So it's the 2D vectors for the road. And here is the, as you see, how complicated environment for the road networks. So 2D, this is used for the training dataset. And here is the road training dataset vectors plus the images on top of images. As you see, this is a very complicated kind of information we have. And luckily, we got some vectors, ready vectors from the topographic database from National Land Service. So it's the kind of open data source for everybody to use. You can download those vectors and download the this also photos, which got from the produced from the area images with the rectified geometry and the radiometric information. So later on, if you are interested in to get such kind of vector data, I can, or you just type from the Google and search National Land Survey of Finland and the open data source, and it will come out the link which you can find where those data sets. And here is the 3D live data point cloud road network from the LiDAR data, and for the training use. And here we got some, so far we got quite a promising result from the deep learning technology, and we detected the buildings, and currently we have produced the buildings covering the whole Helsinki area. And in this project, we started from the very challenging area, like Helsinki area, which have very complicated environment, and also the building style, different type of buildings. So we started from the Helsinki area with using this for the test of deep learning and train a model with those data sets. And we got quite a promising result from the at the moment, and with the F1 score 0.953. So I think it's quite a good result at the moment. And then we also about the road detection, and this is a very preliminary result. We are using the multitask learning technology for the road detection, and this is a very preliminary result. And also currently we didn't have result from the hydrographic features, but I think it will come soon, because for the part of hydrographic features, the task was started from the last May, so it's a little bit late than the other part. So then we got one master thesis done for transfer learning technology for building detection, and then they tuned different part of the unit, and with a different size of data set, and got to the for the test, and they got the quite a promising result, like calculated as the F1 score, as you see with this technology. We use a very limited training or small amount of training data, but we can reach about 0.905 F1 score. So if we consider about the balance, like from the previous model we have trained, which we like use a lot of training data sets, but get a very good result, like 0.953 F1 score. And for this transfer learning technology, and we got basically like 0.905, but with the less training data sets. Then we talk about the most important part of this talk, and talk about problems and the challenges of deep learning in remote sensing and the GIS. And I divided this in the two parts, like problems, challenges in training data, and also problems, challenges in the neural networks. So we talk about the problems in general, not specific, and later on we will talk about the problem in more specific way, which we have in in our autumn project. So in remote sensing field at the moment, there's a lack of a large amount of open training data set, and the formats of the open training data sets are diverse. And with a very little amount of training data set, and also lack of samples in different regions and different times. As I told, like remote sensing data we aim for covering the large area, like the whole surface of the Earth, but the current samples or training data was from the small areas, and it's not enough for getting very accurate models. And from a time point of view, as I just mentioned, and the remote sensing data can be acquired from the springtime, from the summertime, from autumn time, and from a different season, it will be quite different. So in that sense, like currently, I think if we have, for example, if we study snow and then we focus on the winter time, and then we even in national land survey, currently the program is like partly was done springtime, partly was done summertime, because for different data sets and you use for different purpose. But for the training data, we might be lack of this kind of time series kind of training data. And also training data were made in a similar way as the other computer vision tasks, so not specialized for remote sensing task. As I just mentioned, usually computer vision and task dealing with the images with RGB and no other spectrum information. Also, the training data were in a very narrow spectrum band, like RGB, multi-spectral, and hyperspectral training data are needed. So in general, the training data sets are in 2D, so not in 3D. So currently, most of training data in the 2-dimensional. And the lack of uniform classification system. So this is from the GIS point of view. So existing training data have different standard of the classification. So same class with a different name, like grassland and grass, and the same name in different classes, like a farm and land, and the same class with a different type of objects. Also, lack of training data from the diverse spectrums and the sensors. So existing training data typically from remote sensing images with the RGB colors, lack of infrared, multispectral and hyperspectral training data, and the lack of training data from multi-sensors, stereo models, and multi-views data. As we know from our field, quite typically we get 3D information from images by using stereo model and also multi-view with the kind of camera parameters. So it's possible to get the 3D information out of the 2D information, 2D data source. So this is a special technology from our field, like photogrammetry, for example. So currently we are, I think, from the open data source, at least I haven't seen this kind of training data sets available. Then the models with poor generalization ability, because of remote sensing data with the spatial and the temporal characteristics. Like existing training data, a lack of time and the space spans, like location change, season transition. Then problems in general. This is the last one. Also, I think this is quite common with the computer science field. So like existing training data with a different quality of labels, difficult to evaluate, like labels by expert or amateurs, or automatic labels or semi-automatic labels. So the quality can be quite different and with a different standard. So it's difficult to evaluate. Then here is the specific problems, means those problems in our autumn project, which our project team, like they had this kind of problems. For example, like when you're cropping the images and the labels into smaller pieces, so you need to remember to keep them in the same orders, because when you labels here means vectors, actually, like you cut those data sets in the different separately. So you need to keep them in the same orders and checking the cropping result to be sure this is the right overlap to pieces of the data sets and see if they are match each other. And saving the result in the right size. So sometimes you save in the different, for example, especially like images, when you open from the different tools, when you save it, probably it will change different size of the images. So you need to be sure it's in the right size after cropping. And this kind of small details need to be careful. And then label errors. So manually collected the labels, like a building in our case from the beginning of the project, and we had 5 or 6 people from the National Land Survey helping for the collecting the labels like buildings and the road, and we noticed that there are something happened like some errors from the labels like building and the building with this enter this recorded in these labels. So it might also cause a little bit of problem. And also label creation, like to be sure that the object is 1 and the background is 0. And sometimes you do it in the opposite way. So, and combining different types of data to correspond to the same area. So this is sometimes it's a little bit problem when especially when you use this multitask learning, you try to use not only images but also the point cloud. So you need to to combine those different type of the data to the correspond to the same area. And from the labels to the neural network layers and the design, probe date, format, type, size, and the resolution. Especially like for the neural network currently, I think for us the problem is we consider about spatial resolution is a very important indicate factors in the image, like how well this image is defined, like how clearly this image you can see, and we use the resolution. So and in our data sets, it can be quite resolution can be quite different. For example, if we talk about satellite images, the resolution can be like 10 meters or 20 meters or 30 meters, this kind of resolution. But if we use the aerial images, can be like 30 centimeters or 40 centimeters. So it's quite a big difference. But currently, I think this neural network only specifies like you use this network only for this type of resolution, not so it's not very flexible. And also validation dataset selection, and is there some kind of standard how much percent of the percentage of the training data and the test data and the validation data? So in a different case, it might be different. So don't stick to the same percentage for every tasks. And also be careful about computational power. So when you don't have this cloud service, or like us, we have this CSC high performance environment for the training, for the training the model. So if you use a local laptop, and if you have a large amount of training data sets, it might be out of memory. So this needed to be sure, like you have enough computational power when you run deep learning training deep learning models. Then problems in general in neural network. So existing neural networks only consider the image geometry, difficult to take into account the spectral characteristics and the geoscience knowledge. And the lack of flexibility, like a data channel, adaptive optimization, and the scalable memory, and the creation of scalable channels. So this is quite typical in the neural network currently, and we have tested we have not only RGB images, but also we have near infrared channel, for example, RGB and the near infrared channel, like 4 channel of spectrum for the images, and we have tested with different kind of combination and compared to RGB images, and actually there's not so big difference so far. We found we use RGB or infrared RG or infrared GB, and with different kind of combination of the spectral channels, and we noticed actually RGB it's still works the best. So it means like from the neural network, it's not sensitive to this kind of spectral characteristics. So this I think this needs to be considered in like for the further development in the neural network point of view, and to be more useful for the spectral characteristics. The specific problems in neural network, like selecting a suitable neural network for the task. So you need to read the papers and search information, and making tests the way to get into it, and are helpful. And selecting a suitable method of evaluation metrics using a pixel accuracy might be misleading in some cases. So at the moment we are using this F1 score and also IOU as the evaluation metric, how well these models, and figuring out a suitable learning rate, and starting from 0.001 usually typically, and using consistent augmentation methods for training, test, and validation. And if the validation data set is too small, it might cause the spiking to the loss curves. So this need to be keep in my mind in the mind that it might happen during your development. And combining multi-input data in the neural network, and deciding and testing where and how to optimal share data from the different inputs. So this is quite a challenge things, and determining the neural network layers and the parameters and the hype parameters. So finally, because the 2 types of challenges in the Autumn project. First one is related to training and the data quality, and then type 2 is related to the task and the real-world complexity. So when we talk about model training, always come up with the like underfitting or overfitting. This so it need to be quite a challenge, like direct course this underfitting maybe from a sampling strategy, like model does not memorize the training data because of the data augmentation, and the preferable alternative to overfitting. So this kind of need to keep the balance of the fitting. And the indirect course can be training data quality, that incorrect labels increase the data set complexity and the opportunity for improvement. So here's the examples of underfitting. So this blue is the model prediction, and magenta shows the training labels. So you can see the case when the model is underfitting. And the examples of incorrect labels. So it might happen like some part is missing, and the label is not correctly like marked as it is. So it causes some problems during the training. Then challenge 2 is about although the vast majority of buildings are recognizable, there are very few limitations to their possible appearances. So buildings are not necessarily distinguishable from their surroundings, or some of buildings might even not visible. So this case happened because we used the labels or these vectors from the topographic database, and some of the buildings even not visible in the images, but it exists in the database because the municipalities directly got the information from the house owners when they building the house. So they have this kind of drawing vectors ready to be used for the municipalities, and the National Land Survey collect some of the building vectors from the municipalities. So that might happen when some buildings under the trees in the forest, and from the image you cannot see at all, but it exists from the labels. So it might kind of confusing the machine to learn, like from image, even for the human eyes, from the image you cannot see any buildings in the image, but it exists. So this kind of a challenge in our field, like how to estimate this kind of or this might be errors come to the model or the situation. So buildings can have very unique and arbitrary appearances, making it difficult for a deep learning model to generalize to all buildings. So this is quite a challenge also in the case. So here is the some examples. You can see how complicated this environment it is, and so like in some construction areas or some kind of very complicated environment. So how you can make it like right away is the right figure. For example, it is kind of challenge like a railway station. So the mark, this label is showed this is a building, but on the top it's kind of mark of the railway. And
Lingli,
also like
sorry to interrupt you. I just wanted to point out we have 10 minutes to go, and I see quite a lot of questions in the chat.
All right.
So,
yeah, I think this is almost done. Okay, so fast. Yeah, it's okay. I only few slides left. Yes. So this is the kind of parking buildings. For example, here there are some mark here, and it's very difficult to say it's a building or the parking place. Challenge, and this is also challenge construction areas. And here we come to this summary. So as here we have there are a lot of problems and challenges in using deep learning technology for remote sensing and GIS. So it's a long-term task to develop deep learning technology for remote sensing and GIS. So from diverse training data to adaptive neural networks, and the multidisciplinary integration and collaboration are the key to solve the problems and the challenges in remote sensing and the GIS. So that's all what I want to say. And thank you for your attention. And let's go to question.
Thanks a lot,
part.
Lingli. Everybody give Lingli a virtual applause.
Thank you. Thank you.
Thank you. So yeah, as I have pointed out, there are many, many questions. So people are very interested in this work. The first question is, do you have some business figures, like money-wise, how much this automated annotation and updating saves in labor costs, so to say?
All right. I think currently, from the beginning of the project, I have studied about the possibility how to get the labels. I think there are a lot of companies currently working on that. Like basically, we can like outsource this kind of label task to the companies. And there are a lot of options from different countries. But the thing is, as you know, this national landscape of Finland, this kind of data sets probably they don't want to spread to the some countries. Maybe want to because it's with the geospatial location and the tags on the data set. So like every building has the tag, like where it is, you can see from the data set. So in that sense, like we need to consider like where is the server, where you are working for this kind of
So I understand
labels.
it still needs some manual interaction.
Surely. In this project, we have the long-term kind of training work or student work on this for the correcting the result from the network and retrain the model and this kind of tasks.
Okay. So next question would be, how and where do you store the training data? Do you have only pictures in the data set, or also together with the pictures all the meta information, or are these in different databases?
We currently, partly I think we are stored in the CSC environment. CSC ALAS actually it's for data storage, and also from National Land Survey we got 60 terabytes this kind of disk which we can like store our result to our own disk also.
Okay, thank you. So next question was, how critical was the LiDAR data for building and road detection accuracy? Is LiDAR similarly openly available as the orthophotos and the vectors?
Yeah, definitely. LiDAR data from National Land Survey, currently it's open data source.
Okay.
Yeah, you can from the search and you will find different type of data sets, and the LiDAR is one of them.
Very cool. So next question was, in case of classifying the buildings from the point clouds, what data format do you use? Voxels, radars? I don't know the terms. So if you could comment.
Last file currently.
Okay.
LiDAR, LiDAR usually we use the last file.
Okay.
Yeah.
Thank you. So then the next question, has super resolution techniques been tried yet for augmenting the data in the data sets? If it has, what was the effect on the accuracy?
Yeah, augmentation method we have used like the rotation and also the mirror, even the mirror and the rotation and this kind of techniques, and it helps a lot with the final result.
Okay. Next question. Do you use some labeling software to label the objects on the orthophotos, or are they labeled manually? And which kind of output format is the building detection? Are they NumPy arrays or pixel-based results?
Currently, this QGIS is open source, which is currently very widely used in our field. And QGIS you can make the label for the buildings from the orthophotos.
Yes.
So it's
Okay, thank you.
Yeah, and the format you mentioned about the format and the JSON format. Currently, we use the JSON.
Yep. Thank you.
Yeah.
Next question. Have you faced imbalanced training data for deep learning? For example, the proportions of buildings, roads, and farms, they differ significantly.
Yeah, actually, from beginning we had this problem because we had the training data with both buildings and the road. But currently we have separate kind of training data. Buildings is buildings, and the road is the road. But I think it's wise to have the similar amount of the training data for the buildings, the road, if they are in the same data sets.
Thank you.
So yeah, if one part is a large and another part is small, so it's imbalance might happen.
Thank you. So then the next question, what are the hydrographic features you are mainly interested in?
Ditches and streams.
Okay, thank you. Then the next question, are there annual orthophotos in a standard grid? So you can easily compare, for example, summer and winter images of the same area? Or do you have to recrop all images to get comparable images?
Currently, we have images from different years, so we can compare. But currently, we are testing, not in the final stage. We are going to compare, using deep learning technology to detect the features from the old images and compare to the result from the new images. So this kind of comparison, yes.
Yeah. Okay, then next question. In slide 35, is underfitting preferred over overfitting? And could you, if so, could you explain why? So 35,
so I think this is here says why it causes this underfitting, basically. Underfitting, like a sampling problem, and also indirect cause can be training data quality. So this can main reason to cause, and have to keep balance with underfitting and overfitting. Always the problem in training model.
Yes, exactly. Thank you. Next question. What type of companies deal with artificial neural networks? I'm learning them currently, and I'd be interested to working with them somewhere. So I guess there are many companies.
Yeah, many companies. Many company. S3, you can check S3. It's very big, and it's kind of international company, and they located many countries. So you might check this S3.
Yes.
They also work in this deep learning and train the AI model.
Okay, thank you. Next question, which library handles the LAS files? Do you have a library for these files?
Yeah, PyTorch, actually, you can search from PyLAS. You can search, you will find it.
So there's good support.
Yeah, good support for this geospatial data, yes.
Yeah. Then the next question, did you try out to look at the effect? What if you ignore LiDAR? So is LiDAR data really crucial to get good accuracy?
Yes, LiDAR data, it's because it's a 3D data with the height of the information. So it's very important in that sense, because we compared with only use the images or with height information, and then with height information, so the result like accuracy improve a lot.
Yeah. Okay, that's it. The last question you already answered about the imbalance data. You look at different objects separately or different categories.
Yeah, at the moment we have, but later on that could be like we have put a different class in one training data set, so it might have this imbalance problem. Yes.
Thanks a lot again, Lingli. Yeah, and if you have any openings for master thesis topics that I should forward to the students, let me know. I would be happy to forward them.
Definitely.
You have a lot of challenges, so a lot of possibilities to work.
Yeah, surely. I think we have a lot of topics for master students. So welcome if you are interested in, and please contact us. And we always have a position open in National Land Survey for this kind of master thesis work.
Very good. Thanks a lot again, Lingli, and have a nice day.
Thank you.
Bye-bye.
Thank you. Have a nice day. Bye-bye.